Warning, the video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes.
All right, so here's a great related rates example. It's a terrible drawing by me because I'm not an artist, and I never said I was. But a boat is being pulled into a dock by a rope. Red is the rope right here, okay? And the question is, how fast is the boat approaching the dock when it's 2 meters from the dock? Now, I have to give you some extra information here. First of all, the pulley that the rope is being pulled over is 1 meter tall. Also, the bow, I guess the front end of the boat here, is at the same elevation as the pier. Okay, so these are the same elevation right here, which creates a right triangle. That's kind of important for this situation. And we're going to be pulling this rope in. Let's just pretend that we're going to pull the rope in, pulling the rope at a rate at 1 meter per second. You can actually use any number you want. It doesn't really matter. But let's just say that you're pulling the rope by 1 meter per second. So 1, I've read the problem. 2, I actually have created a diagram, so I understand what's going on. I have this boat, I'm pulling towards the dock. I'm pulling the rope at a rate of 1 meter per second, and therefore the boat is getting closer and closer to the dock. I just want to know how quickly is the boat closing in on the dock when it's 2 meters away. Okay, so I definitely think I understand. Let's go ahead and label some things here. So let's see, I'll call this, I say this, but I mean this distance right here. I will call that distance, and in fact I should dash it out completely. I'll call this dashed distance D. Or maybe I should call it H for the horizontal distance, and I'll call this R for the rope distance. Okay, it doesn't really truthfully matter what you call it. You call it anything you want. But that, let's just pretend that forms a right angle there. So I've labeled some things. Let's see, what were we given? Actually, it's easier to say what we want. What do we want? Well, we want to know how quickly the boat is coming towards the dock when it's 2 meters away. So we want, how quickly is that H changing when H is equal to 2? That's really what you're asking. You want to know how quickly that horizontal line is changing when you stop time at when that H is equal to 2. And then let's write out what we're given. We're only given actually one thing: the rate of change of the rope length. We are decreasing that length by 1 meter for every second. It's decreasing because we're pulling the boat in. These concepts are very critical for you to understand. So you need to really get a physical understanding of the situation. So, okay, labeling, I think I feel pretty good about that. Step 4, I need the master equation. What is the equation that relates R to H? And you could easily see it here. It's yet another Pythagorean theorem. This happens quite often actually with related rates problems. So the master equation here is going to be that H squared plus 1 squared must equal R squared. Now I'm going to go ahead and take the derivative. Master equation is done. Let's go for the rate equation. Remember, you're not substituting in any constants until you're done with the rate equation. You might say, but wait a second, you substituted in 1. Well, yeah, that never changes. But what I'm saying about substituting in constants is I'm not going to let H be 2 because I don't want H to be 2 always. I want to stop time when H is 2. So I want to take the derivative and then let H equal 2. If that doesn't make sense, I'm sorry. Take the derivative of both sides with respect to time. So the derivative of H squared is 2H dH dt. The derivative of 1 is 0. And derivative of R squared is 2R dr dt. You could divide both sides by 2, because I think it's very healthy to do that. And now you're back to basically the previous problem, which I sort of regret, because I don't want you to feel like I'm only choosing problems that have Pythagorean theorem. That's not my intent. But let's see what happens. So now comes the sub-in step, sub and solve. So we're going to let dr dt equal -1 and h equal 2. So let's see, this implies 2 dh dt is equal to r times a -1. Or in other words, dh dt is equal to a -1/2 r. But r is the rope length, and we need to know that rope length. Luckily, h is 2. So I just have this little right triangle. A little over accentuated, but whatever. Like that, and I can easily see this is going to be √5 is the rope length at that instant. That's a right angle right there. So √5 is what r is, -√5/2. So what does that mean physically in this situation? Well, I'm grabbing a calculator, so give me a moment. There we go. So it means that the distance between the front of the boat and the dock is decreasing at a rate of 1.12 meters per second when it is 2 meters away from the dock. Really a very cool problem.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at ease. Says, listen close. Don't talk too much that isn't cold. Sure, you may really hurt inside. It doesn't justify you to speak too loud and cry.